All right. All but three of you have been introduced to this idea of oxidation and reduction in your first year course. I don't believe you had anything on this. You may have. Was it last year? You three were last year with Homan? I believe. Oh, you were 2 years ago? Were you last year? And you were last year. I think last year he may have briefly mentioned the concept. You may not remember. I don't believe he did anything when you... I don't believe so. Do you remember it at all? Oh, well then maybe he did. Okay. With my regular chemistry students, of which there's like 4 or 5 of you in here, it was also briefly mentioned, but never really gone into in detail. I think we talked about what oxidation meant, what reduction meant, what was happening in that process. Okay. With the honors students, we actually learned how to balance equations using the oxidation numbers and such. Does anyone vaguely remember this?
Oh, yeah.
Oh, I get that. I get that. So as it turns out, when you guys were in your first year course, you all learned 5 or 6 different types of chemical reactions: synthesis, decomposition, single replacement, double replacement, combustion, and then acid-base neutralization is just a type of basically double replacement reaction, if you think about it that way. So far, so good? All right. All of those actually all fall under the idea of an oxidation-reduction reaction, with the exception of the double replacement and or the acid-base neutralization. What that means is electrons are actually being transferred from one species to another. Okay? So, to kind of give a little bit of terminology here, the process of oxidation refers to the loss of electrons. So if something has oxidized, that means it has lost electrons. Therefore, its oxidation state becomes, and I emphasize this next word here, more positive. That doesn't necessarily mean it becomes positive. It becomes more positive. Or sometimes it actually is easier to look at it as less negative. So going from -7 to -5, oxidation, it became more positive or less negative. So far, so good? Okay. Now, you guys hopefully understand why that's true, because we've lost electrons, and electrons have a negative charge. Okay. Well, I think you guys can figure out what goes on then with reduction. Obviously, that's going to be the gain of electrons. Those electrons have to go somewhere. It may not happen today, although it might. It's definitely going to happen tomorrow. We're actually going to use the transfer of electrons to help us balance the equation. Okay? Because you guys may remember back when you first learned to balance equations, some of them were kind of hard to do. You thought you didn't know where to start, and you kept having to go back and forth and back and forth. Well, using if most of those, the ones that you had troubles with, were probably oxidation-reduction reactions. Okay? And what we're going to use is this number of electrons that are transferred to give us a good starting point. Okay? Because then it's just a matter of just fixing things up from there. Anyway, so we're going to gain electrons. Where are those electrons going to come from, do you think? The species that oxidized. Okay? And then, in this case, the oxidation state becomes more negative. Now, again, I'm going to emphasize that it doesn't necessarily become negative, it becomes more negative. So, for example, if we see an atom that goes from a +3 to a 0, it has reduced because it became more negative or less positive, whichever way you want to look at it. Hunky-dory so far? All right. The thing that we have to do now, and this is actually the key to the whole thing, is what is this oxidation state thing? Well, in many times it actually agrees with the charge of an ion. Now, what we're talking about when we say something has oxidized or something has reduced, we're talking about individual elements or individual atoms. Have they oxidized or reduced? We're not talking about compounds. Okay, so it's individual atoms that oxidize or reduce. These atoms are actually within compounds, clearly, or most of the time. Okay, so if you turn in your books to page 177, I want to, and again, it's not necessary that every single person has the book, but if you can at least have enough books to go around and share. Has anyone ever, just out of curiosity, has anyone accessed the online version yet? Okay, you guys know that there is one? I mean, that's why I signed you up for at the end of last year. Okay, well, if you would like to be able to access that more often, let me know, and I'll go over how to do that. Okay, I may have lied. Why did I say page 171? Well, that would be why. Good. All right. In my opinion, I don't know, just like any other textbook, they've got a pretty good set of things here, and then it's a little vague in some cases, but then they put this little thing over here. It's pretty good. Anyway. Top page 177, it says rules for assigning oxidation states. And this is basically what this is, a bookkeeping kind of thing. Is this what's actually going on? Maybe not necessarily, but it allows us to keep track of where the electrons were and where they're going. Okay? It's not an absolute, though. And then notice, within the parentheses, it says these rules are hierarchical. And then if any two rules seem to conflict with each other, there's going to be a couple times when they seem to, you follow the rule that's higher on the list. Okay? So, here we go. And this, for many of you that have had me the last 2 years, you'll recognize some of this. The oxidation state of an atom in a free element is 0. They give you a good example there. They give you copper, which is an elemental metal. And they give you Cl2, which is a diatomic element. In either case, the oxidation state is 0. Number 2, the oxidation state of a monatomic ion is equal to its charge, which makes sense. These two are easy. Thirdly, and we've used these first 3 rules to kind of help us name and write chemical formulas up to this point in your lives. Okay? The sum of the oxidation states in a compound is equal to 0. And if it's an ion, it's equal to the charge on the ion. Those two ideas right there are going to help us out a lot. Because what if we don't have a monatomic element? or a diatomic? What if we don't have an element? What if we, and you're going to see a little list of things where you're going to say, oh, these are always this, these are always this, these are always this. Well, what if it's not one of those? Well, we're going to use that idea that the sum is going to be equal to 0 for a compound or equal to its charge for an ion. Okay, so looking at the water example, okay, what is the charge on the oxygen ion? Always. Well, not always, you're going to find out. Typically it's -2. Hydrogen you know as +1. So we have 2 hydrogens, 2 positive charges, 1 oxygen, 2 negative charges equals 0. Whereas with the nitrate, and here's a good example, oxygen is typically -2. Okay, there's 3 oxygens in the nitrate ion. Therefore, what's my total of negative charge? 6 negative charges, right? The whole thing has to equal -1. Therefore, in this case, the nitrogen has to be +5. And that's how you do that simple math. Okay. In their compounds, metals have positive oxidation states. In compounds, metals have positive oxidation states. Group 1 metals are always +1. Group 2 metals are always +2. Now remember, this is hierarchical. There might be a scenario where that may not be true. Okay? Number 5, in their compounds, non-metals are assigned oxidation states according to the table, which is immediately to the right there. Fluorine is always -1 in a compound. What is the one exception to that? I'll let you guys think about that. There is one exception, and we have to go back up to number 1. F2. Okay, that's the only time fluorine's not -1. So that would be our possible first application of that hierarchical thing. Okay, so anyway, fluorine's always -1. Now, why is fluorine always -1? You guys have had enough information in your lifetime to help answer this question. Highest electronegativity, right? Okay, which means it's very, very small. It's one of the smallest elements for the reasons that we learned about your first class. And 2, it has a fairly highly charged nucleus for its row. For its row. Okay, in fact, it has the next to highest charge. It's got 9 protons, right? So there's a strong attraction for those valence electrons, for all the electrons. Yes? Help her out with that. I'm sorry, what's that again? Okay, let's do this. What she meant by that, I'm going to check here in a second. You meant by the radius, the size. You're saying the size of the atoms get larger as you go across the periodic table. Everyone agree? I understand that, but I'm using your question to remind everyone. What happens to the size of the elements as you go across the periodic table? They get smaller. Why is that? I already gave you I just got done giving you the answer. What's that? More protons. Remember, all the electrons are in the same energy levels as you go across the period. Okay? The only thing that changes is the number of protons. Back to Coulomb's law, greater number of protons, greater force of attraction, smaller. No. There's more protons. Okay, that's why we do these things. All right. So anyway, yeah, we're still looking at the, well, kind of. Now, the tables, in the most part, should make sense to you guys because you've seen this before. Okay, fluorine's always -1. Hydrogen is almost always +1. Oxygen's nearly always -2. The group 7As are -1, the halogens, which you guys know that. The group 6As, the chalcogens, are usually -2. And the group 5As are typically -3. However, there are exceptions. That is also hierarchical. Anyway, moving on. Looking at number 5. Keep these points in mind. Oxidation state of any given element generally depends what other elements are present in the compound. Rule 3 must be always followed. I've already mentioned that, where the sum has to be either 0 for a compound or equal to the charge for an ion. And then once again, I've already mentioned that you use Rule 3 to deduce the oxidation states of other elements that haven't been covered by everything else. Carbon, this happens to carbon a lot. Carbon does all kinds of different things, and it kind of depends on what else it's with. Okay, that one will end up causing you guys a little bit of consternation as we go along. But wait, there's more. You have to turn the page. Okay, these are just more types of applications here, okay? But looking at carbon dioxide, in example D there, which of the elements do we know nearly always? Well, as far as you guys know, always for right now. Oxygen. Well, there's 2 oxygens. So the oxygen, there's 2 -2 charges, therefore -4. That means in this case the carbon must be +4. In E, looking at the sulfate ion. Once again, the oxygens are -2, so we have 8 negative charges, therefore the sulfur must be +6 because of the charge of the ion. Now, this next example is the one that you need to be aware of. K2O2, which is the one that we always know. It's the potassium, okay? Because that goes back up to item number 4. Okay, rule number 4: Group 1A metals always have an oxidation state of +1. And remember, it's hierarchical. Okay, the oxygen doesn't come in until item number 5, rule number 5, with the group 6A thing. So, with that in mind, each of those oxygens must now be what? -1, right? So, if the O2 has a charge of -2, what do we know that as? Go ahead. The peroxide ion. Remember you had to learn that one as one of your polyatomic ions when you took chemistry? Okay, so there's a good example. So oxygen's always -2 unless it's a peroxide. When does it behave as a peroxide? With what other elements does oxygen act as a peroxide? Can oxygen act as a peroxide? What's that? Group 1A and Group 2A. That's the only time oxygen can behave as a peroxide. If it's with if it's okay, so for example, the reason I'm bringing this up because it happens quite a bit. Almost all of you are familiar, well, maybe not. Almost all of you are familiar with this. H2O2. It's in your brown bottles at home. Hydrogen peroxide, okay? There's one example of that. This is also a relatively common substance, which we would call sodium peroxide. What about this? This is manganese 4 oxide. What's the oxidation state of the oxygen? -2, like it normally is. What's the oxidation state of the manganese? +4. You guys following? That'll cause some people at first to kind of, hey, isn't that a peroxide? It's O2. No, because it's not a group 1 or 2 element. Okay. That is about it, other than practicing this a little bit. I'm going to throw some at you to practice a little bit here. So here we go, digging into the freshly created notes. Freshly. What we're going to do is find the oxidation state of each element in the following substances. Now, just as a reminder, better do this. So we got 9. Just as a reminder, this is what I want you to do, at least for now. Let's walk through this one real quick, because this is probably the easiest one on here. Does anyone know the oxidation state of either one of these elements right off the top of your head? Fluorine is -1. So what you would do is somehow indicate that it's -1 each. Each of the fluorines is -1. Therefore, the sulfur would be +4. So for now, kind of get in the habit of doing things like that. I'll let you guys do this on your own for a small amount of time here. Ooh, I should give you that one. No, we'll do that as our example. Okay. Many of you have had the opportunity to go through this before. The notes I'm giving you right now aren't really a whole lot different than the notes I gave you whenever you had me before. This is the key to everything, though. Okay, you can't move on unless you get this done. The other thing I want to say is some of you may not pick it up as quickly because, one, you've either never seen it before, or two, you kind of forgot a little bit. Either way, it's okay. You're going to get it within like 2 or 3 days or less. It'll happen. We get a double period tomorrow too, don't we? Awesome. We're going to be done with redox. I'm sorry, what? Okay, thank you. Awesome. We're going to be done with redox. We'll get the next lab introduced. We'll do the labs. Shoot, we may not get to them until next week. How many weeks do we have left? 3 in the quarter?
2.
Is it just 2? This week and next week?
And some of the next ones.
Okay, thank you. 3 weeks. Yeah, we'll get this done. We'll get through electrochem. Plus, we'll get all the labs that I want to do in. We didn't get that done last year. Discovered 2 years ago that if I walk away without a range of this, the video stops. So I have to learn to. Plus, when Owen and I start making that to Jason, we don't want the whole world to know that. I'm sorry, okay. What is that? Okay. Any other quizzes didn't make my way up? Okay. There's one. Oh, this is my other group. I don't know what I did with this stuff. This is a chemistry quiz. Okay, we ready? You may not be all done, but let's do it anyway. Let's start off with an easy one. Do we know any right now? Potassium is going to be +1. Are there any others that we feel highly confident in? The oxygens are going to be -2 each. Therefore, the manganese is +7. Excellent. Let's go over here. Are there any that we're fairly confident in? Oxygens, which are -2 each. The whole thing has to equal -2 therefore the carbon must be +4. Just for fun, let's go to the Methane. Are there any that we're highly confident in? The hydrogens, which are +1 each. Therefore, the carbon must be -4. Look at that. Yeah, well, wait, there's more on the carbon. All right, moving on. Over here, are there any that we're fairly confident in? Which are +1 each for a total of 4 positive charges. The whole thing has to have a net charge of +1. Therefore, the nitrogen must be -3. Which, if you remember, when we were looking at the nitrate ion, the nitrogen, I believe, was, in one of the examples in the book, +5. Okay. I don't know. Do you want to go here or not?
Yeah.
Okay. Are there any that we know for sure? The sodiums are +1 each. Therefore, each oxygen must be -1. She was on her phone. Don't worry about it. I think that's incredibly ironic that she just yelled at you. That's very good. All right. Which one do you want to tackle next? I2. Okay. Iodine. 0. Good. Got that one done. Now which one do you want to tackle? Okay. Here we go. Are there any that we know? Okay. The hydrogens are +1 each here and here. Anyone else? Okay, there you go. The ammonium ion, so you guys recognize that, right? The ammonium ion has a 1+ charge. If that's the case, then this nitrogen must be -3. If this is a 1+ charge and there's 2 of them, this whole thing must be -2. Would you guys agree? Okay. Therefore, the next easiest one would be the oxygens, which are going to be -2 each, which makes our phosphorus have to be +5. Okay. So sometimes in an ionic compound such as this one, we actually have to look at the charge of the ions to help us figure out what's going on. Which then brings us to the pièce de résistance. Are there any that we know? What are the oxygens? Which gives us a net -8 charges. Have to have whole numbers for oxidation states. That would not be a whole number. Go ahead.
Two of the irons are iron 3, and then one of them is iron 2.
There you go. Because remember, the 2 choices for iron, the 2 possibilities for iron, well, 0, or, because if it's elemental, it's not. Okay, so the other 2 choices are iron 2 or iron 3. Somehow or other, we have to get to 8. So 2 of them are going to be iron 3, one of them is going to be iron 2. Yes?
What would you call that compound?
Rust.
Well, you would say like iron 2 for things like, I already talked about copper 2 nitrate or something like that.
I got that. You would. Right. It's got its own special name. Well, we're done with that. Okay, so now that we seem fairly confident in the ability to determine oxidation states, the whole point of this is, 1, to use that type of information to help us determine whether a chemical process is a oxidation reduction reaction, 1. 2, to use that information to help us balance the oxidation reduction reaction if it is. Okay? You seem to be packing up. How do you know this? It's 10 o'clock. Look at that. It's going to ring in 3 seconds. Well, it's a good place to start tomorrow then.